How weather forecasts actually work. Explained simply. Most people check the weather without thinking about it. You open an app. You see a sun or a cloud, a number for temperature, maybe a percentage for rain. And somehow, it often feels wrong. The forecast said sunshine, but it rained. Or it said rain all day, and nothing happened. So the question becomes simple. How can we predict the weather days ahead, but still get it wrong so often? To understand that, you first need to know what a weather forecast really is. A weather forecast is not a guess, and it's not a promise. It's a calculation, a very large one. Every forecast starts with a snapshot of the entire atmosphere, not just where you live, but everywhere. Temperature, air pressure, humidity, wind speed, wind direction, all measured at the same time. This data comes from thousands of places at once. Weather stations on land, buoys floating in the oceans, weather balloons rising high into the sky, radar systems tracking rain and storms, satellites watching the Earth from space. Every few hours, all of this information is collected. This becomes the starting point. Think of it like a freeze frame of the planet's atmosphere. Now comes the important part. Meteorologists don't predict the weather by intuition. They simulate it. They take that snapshot and feed it into powerful computers. These computers run mathematical models that describe how air moves, how heat flows, how moisture turns into clouds and rain. These equations are based on physics. The same physics that explains why warm air rises, why cold air sinks, and why pressure differences create wind. The computer then asks a simple question. If the atmosphere behaves according to these rules, what happens next? Then it calculates, minute by minute, hour by hour, day by day. That's a forecast. But here's where things get interesting. The atmosphere is incredibly sensitive. Tiny differences at the start can lead to very different outcomes later. A slightly warmer patch of air, a small change in wind speed, a bit more moisture than expected. These small uncertainties grow over time. This is why today's forecast is usually very accurate. Tomorrow's is still pretty good, but next week's becomes blurry. It's not because meteorologists don't know what they're doing. It's because the system itself becomes less predictable. This idea is sometimes explained with a simple metaphor. The butterfly effect. The idea that a very small change can eventually influence a much larger outcome. Not literally a butterfly changing the weather, but the principle behind it. Weather models deal with this uncertainty by not running just one forecast. They run many. Each model starts with slightly different assumptions. Small variations in temperature, pressure, or wind. This creates a range of possible futures. Some scenarios show rain, some show clouds, some show sunshine. When your weather app says 40% chance of rain, this is what it really means. In 40% of the simulations, rain occurred at your location. It does not mean it will rain for 40% of the day, and it does not mean meteorologists are unsure what rain is. It means the atmosphere could reasonably evolve in more than one way. Now, you might wonder something else. If weather is so complex, how do forecasts work at all? Why aren't they completely random? The answer is scale. Large weather systems behave more predictably. High-pressure systems, low-pressure systems, jet streams. These features move slowly and follow physical patterns. That's why we often know days in advance when a heat wave or cold front is coming. Small-scale events are harder. Local showers, thunderstorms, sudden wind gusts. These depend on tiny details that are difficult to measure everywhere at once. That's why two towns close together can experience very different weather on the same day. It's also why forecasts are constantly updated. Every new batch of data creates a new snapshot of the atmosphere. The models are run again. Predictions are adjusted. Forecasts are not static. They are living calculations that evolve as reality unfolds. Different countries and organizations run their own weather models. Some focus on global patterns. Others specialize in local detail. They often compare results and look for agreement between models. When many models point in the same direction, confidence increases. When they disagree, uncertainty grows. This is why extreme weather warnings sometimes change at the last moment. Not because someone changed their mind, but because the atmosphere revealed new information. There's another common misconception. People often think forecasts are worse than they used to be. In reality, the opposite is true. Modern forecasts are far more accurate than those from decades ago. A 5-day forecast today is roughly as accurate as a 2-day forecast was in the 1980s. Better satellites, better sensors, faster computers, better models. All of this has improved reliability. But expectations have changed too. We now expect hour-by-hour precision for a chaotic natural system. And that's where frustration comes from. Weather forecasts don't fail because science is weak. They fail because the atmosphere is one of the most complex systems on Earth. And even then, it's remarkable how well we understand it. So the next time the forecast seems wrong, it helps to remember what it actually is. Not a promise, not a guess, but a snapshot of countless possibilities, filtered through physics, data, and probability. That's how weather forecasts actually work. Thanks for listening. Did you already know this is how it works? Or did something surprise you? And if there's something else you've always wondered how it works, leave it in the comments. Till next time.